Okay, so welcome back to our series on the cool programming language. And yeah, like so far we actually managed to implement the front end of the compiler and also what's called gatekeeping. I saw that's what they call it on Wikipedia for some reason. I don't know why. And yeah, basically the front end was just doing the lexing and the parsing for the language. And basically, as an example, the lexer is obtaining all of the tokens from the language. So, splitting, let's see, basically an example. So let's go with the one that I always use as the main one. So we have the language itself, which is something similar to Java in a way, because it has classes. I mean, if it has classes, it's similar to Java, obviously. But it has like a lot of other cool stuff, like let expressions and cases. So, it's not really like Java then. It's more like a combination of Java and some functional programming stuff. Although it also has for loops and while loops, so it's still decent language. So yeah, like the Lexer will just take all of the tokens and split the language into tokens. Then for the second part, what we did for the front end was to get the AST out of the language, and then for type checking, which is the next stage, I guess it's not really included in the front end because not all of languages have static type checking. Like Python, for example, is dynamically typed, but like it's the semantic checks, and yeah, let's use an example for semantic checks, which shows errors. So at this stage, we rule out all of the programs that can contain errors in some idea. And yeah, like the plan for today is to actually get this AST to have also types on it. So for example, I can already show that as the result. So we want to get the types for each expression, right? And then the next step would be to generate some sort of intermediate representation, because going straight from the AST or like the language itself to assembly is a bit difficult, so we might need some intermediate representation to help with that. And I mean, the types on all of the expressions are the first step in being able to do the intermediate representation, so that's why we need that. But that's pretty easy to do because we already did type checking, so we already have the types, but we just need to add them, like save them on the AST, because we don't do that. We just use type checking to show errors, right? So yeah, we just use type checking to show the errors, but if a program actually works, we don't really do this yet, right? So we just need to also store the types on the AST, because currently the AST, like at this point, basically, if you think about it, it's just this. But after we are gonna go through the code and implement stuff, it's gonna make it look like this. Also have the types on the AST, so that's nice to have. And yeah, I guess that's the first part, because I split the video in like maybe two parts. I guess the first one is getting the types on the AST, like evaluating, not really evaluating because we don't interpret anything, but we do type evaluation. I guess it's what it's called. So we evaluate the types, and yeah, we are gonna annotate the AST. That's the first part. And in the second part, we are gonna generate the intermediate representation. And the intermediate representation that we are gonna use, it's called tree address code, and I thought that it's really similar to assembly. So yeah, because I guess they can say whatever on Wikipedia, but here they say that the three instructions translate more easily to assembly language. So yeah, what's a tree address code expression? I guess that's a good question. Well, we have in their example they have this math expression, and they want to make it more easy to convert to assembly language. So probably they have a parser, it converts it to some AST, and then they are able to split it into a lot of really small expressions. Like that's the main idea, because it's easy to go from an AST to this kind of list of instructions. And yeah, I mean, I can say that because it was not really difficult. I mean, it worked almost first try. If you think about it, if you ignore all the segmentation faults and compiler errors, then it was first try. But yeah, I guess we can see some examples to understand a bit the idea of tree address code. So the easiest one, the first one is, well, how will it work is obviously it works for expressions. So the classes and the functions will stay the same, but inside of the body of the function we can run this tree address code generator. And yeah, like the easiest example is just simple variables, identifiers. How will you convert them to tree address code? And that's a good question, and it's, you know, just the variable itself. Don't do anything on it. That's the base case, let's say. And the same thing for integers. I guess it's almost the same. It's like a trick question, because if you want to use that integer somewhere else, you might require a variable for it. So we create a variable for that int, and then we just return that variable. So that's the main idea for int literals. And we can look at more complicated stuff like additions and stuff. So for addition, this is like the math operator from here. And yeah, let's take a look. We just generate integers for all of them, see, and based on the AST we just add these together. So if we, I guess I can try to generate the AST. Let's generate the annotated one. So it was in TAC 003. So the AST is pretty huge though, but it looks something like this. We have an addition between 1 and 2, and then an addition between that result and 3. So here we do 1 plus 2, and then we do the result plus 3. So that's the idea of tree address code. And probably we'll see more complicated examples along the way, but here is one for a for loop, which I think we don't have for loops, but it can be a good example to understand how to implement control flow operations. So here they evaluate the predicate, right? But in this case they do like a not predicate. They do the reverse of this check. And if that's true, they go to the label 2, which is at the end, so they skip everything. But if this is not true, then the jump doesn't happen. So they are gonna come and solve the body of the for loop, and here is a unconditional jump that goes back to the predicate checking. So yeah, I guess this is a pretty good example to understand how to do control flow. I mean, this is gonna come in handy for the while loops, but like if statements are pretty similar in a way. Yeah, and the hardest one will be case statements because they require a lot of branching, but I mean, it's still pretty decent. So as I said, there are gonna be two parts. I guess a bit more like three parts because the first one is gonna be adding the types on the AST. The second one is gonna be the simple um, instructions, like non-conditional ones, and the third part is gonna be the conditional instructions, like solving the conditional ones. Um, like in this case, solving the simple expressions and then solving the conditional ones. So that's the main idea. And after we are gonna get this tree address code going, we will be able to finally start on getting the assembly code. So yeah, I guess now I'll leave you to past me that was implementing the stuff that I said. So okay, so for the first day, the plan was to add types in my AST. Here I was just checking around how it looks on the main file, which works. And yeah, I added a character pointer in the AST expression, so we'll have types only for expressions, but that's enough to have types on basically everything. And at this point, I was just thinking, well, how can I display the types nicely, right? Like here I initialize it with null, so it's like at some point we have to initialize all the types in the semantic checks. But yeah, now the like my issue was how can I guess print the types nicely on each expression. Like you'll see that now I was trying to experiment with that. I went basically to the int type and like yeah, if the type is not null, then just print it, you know. And here I was mocking it with x in parentheses, so that's how it I tried to make it look like, but I didn't really like it. It was a bit weird. And I also noticed that I haven't initialized the type everywhere. So yeah, I went back to the parser where I create each expression. And I was thinking, well, I initialize the type there, like I make it null. So what can happen, right? Like where do I create another expressions? And I found that basically in binary expressions, I create another expression. So that was not initialized, right? So the type was being a random value. So at this point I was thinking, well, should I change the mallocs to callocs? And the difference between that is calloc initializes everything with zeros, right? It also does a mem set to zero. But I was like, yeah, I don't know why I didn't do that. It would have been easier, I guess. But I just went ahead and added this type equals null everywhere where I initialized an expression. So that's one way to do it. Yeah, I mean, obviously it would have been easier to use calloc, but this also worked. But yeah, at this point I was like, yeah, I don't like to use the parentheses version because as you can see, the types can look a bit messy. Like you don't really know which type belongs to which expression. So yeah, I was thinking what would be a better way to do it. And I think, well, let's see if I figured it out yet. I was thinking, well, I can put a type right after the expression, but that means I have to edit that in almost all the places where I do prints. And I don't know if it's too difficult, but in the end it was much worth it because it looks, I mean, in my opinion, it looks a bit better to have the type on the same line as the expression. It makes it more obvious where it comes from. So yeah, you can see here I changed it to, well, if the type is not null, then you print a colon and then the type, right? And then you have to put the new line. So that's why I was thinking, well, I have to edit that in all places. Like, don't forget about the new line. You have to delete, and like you have to put a type between the expression and the new line, right? So just copy paste everything now because yeah. I don't know why I was wasting time there. But yeah, just copy paste everything. Um, now I forgot about the new line, but I'll delete it later, so it's not really an issue. And yeah, basically on each case we have to. Yeah, I mean it's more about making the AST printing look prettier, right? Like to give more information to whoever is using the compiler about the AST. And I think, yeah, probably this method looks the best. So yeah, here it was a bit different because it was for a branch, but it's still pretty much the same thing with having to display the type on the same line as the expression. So yeah, let's see, because here I was really close to finishing that. Yeah, for methods, like method call, I was thinking a bit longer, but um, there was really nothing to think about because you only have to show the type for the function call itself, because all the other expressions are accounted for in the other, eh, like on the other branches, right? Because each argument is basically an expression, so that was accounted for. So here I was like checking that everything still works, because you never know how you can introduce a small bug. And yeah, now it was time to annotate the AST from the semantic checks. And to be honest, I was trying to search for like the easiest way to do it, and at first I didn't get it, because I mean, of course, um, so yeah, like my idea was, instead of returning directly, let's create a variable, and that variable will hold the type that's returned by each of these checks, right? Because how I made the semantic check was, you check the expression, and after you check the expression, you return what type it got, right? So if you do a 1 plus 1, this expression is gonna return an int. So our static check function will also return an int. And you can reuse that type in the following, like in the higher expression from the AST. So that was the idea. And yeah, I think at this point I um, use this type everywhere. Obviously, I forgot about the break, but I'll do another pass over all of these cases and add the break. And yeah, just say that the type of the expression is the type that we got from the check. So that's easy. But now I was like, well, I can see that we're missing some types. For a sign, for example, you can see that there's no type after the arrow. So at this point I was a bit confused, because why? Like here you can see that we get the types back. So it's not that we don't return the types correctly. It's somehow that when we assign the type, it doesn't stay assigned. Like, if you get what I'm saying. So yeah, here I was just really confused about that. But let's see if I manage to find it. How fast did I get the bug? So like the issue was that here I was sending, like, in some places I was getting the value using dynamic array get, but I should have gotten the reference, because we want to change the type on the expression, but if we get a copy from the array, then we wouldn't be able to change the type, because if you change the type on a copy, it is changed on the copy, it's not changed on the main object. So that was the issue. I had to use almost in all places. I had to change the array get with array get ref from because yeah, array get just gets you a copy. It does a mem copy inside of the function, and array get ref actually doesn't do a mem copy. It just gives you a pointer inside of the array. And yeah, this function is from the small library that we implemented from ds.h data structures basically. And yeah, at this point I was just debugging everything, making sure that I use the right addressing, I guess, and yeah, taking the reference to the objects themselves. So yeah, here I was just trying to create a test case just to figure out if I get, you know, the right answers. So here for local, for example, it was fine. Then for the case statement, let's see. I think I guess it was still fine. I don't remember exactly. Well, yeah, the case branches were fine, but the case itself, it was missing the type. So again, I had to go back to semantic check and see where I was not using the reference. So probably here in semantic check expression for case, I was doing, well, I was taking the method not as a reference. Well, the method body, it was not a reference, so it was not being saved. But also the method, it was not a reference, so that's also an issue. And the other issue with C is obviously when you change something from a value to a pointer, you have to change in all places the dot with arrows, and that's the most annoying thing about C, I guess, that you have to use different what would you call them, operators, I guess, for accessing fields in structures, depending on whether you use, I guess, the pointer or a value. Like that's pretty annoying. And yeah, here I was going through all the dynamic array gets and thinking which ones should I change to ref. And the point is, if what I'm trying to get from the array is part of the AST, it should be a reference. If it's anything else, like, you know, from the context, like the type environment or something that's useless, or I mean useless in the sense that I use it just for type checking, not really, I don't want to change that value, then it can stay as a dynamic array get. But yeah, for everything that's on the AST, it should actually be get reference. So here, for example, for branch, again, it should be a reference, but it could also stay as a simple copy because it's actually a pointer, because it's a dynamic array itself. So that can stay as a value, but I thought, well, just to stay consistent, let's change it also to reference. Why not? And yeah, here you can see that I had to change all the functions from values to references. And yeah, now it should work for cases as well, so that's good. Here yeah, I paused a bit because this is a context, so we don't care about getting it as a reference. It's from the typing environment, so that's good. But here, for example, for the block, we have a list of expressions, so we get the reference to them. Here this was for the dispatch, this was for the full dispatch. Yeah, so some of them can stay as values. For example, class can stay as a value. But again, just to be consistent, I'll also change that to pointer. And yeah, here just checking that everything has a type associated with it. Here for outstring, I was like, why does why is there a new line? And it's actually because we just print a new line. So the string that's shown in the AST is a new line, which is funny, but yeah. So yeah, here, as I said, I changed this to a reference, although it wasn't really necessary, but it makes it more like the other stuff from the AST. Like everything is a reference now, I think. Probably there are some stuff that needs changing, but if I remember correctly, I did all of them. Oh, that was rough. I forgot to use the right function there, so everything was failing. I guess we were getting a lot of segmentation faults at that point. And yeah, at this point I was thinking, well, why not just create a new list of test cases for semantic? Because in the checker we can specify a folder for the tests and the type of compiler to use on those tests. So it would be pretty easy to just create a new folder with all the new tests and run the semantic checks also on this folder. So I just deleted all the references from the old one, and now I had to fix all the like typing bugs that are in the cool programs. So just remove everything that has an error, and pretty much that's the main idea from now on. We just go through all the test cases and remove everything that throws an error. And also we have to check that the typings are right, and we save those as references, the outputs. I mean, the best way would be to do it manually, but or like what I would do if I wanted to be 100% sure that everything is right, maybe run the parser on the AST, like generate the AST without types, and then add the types manually. But I mean, come on, that's boring to do. I guess um, just looking at a few types, seeing if they are right, and saying, okay, I guess all of them are right if two of them are right. So yeah, just going through all the test cases, fixing all the errors that appear due to semantic checks, and then after that we are left with an annotated AST. So we just have to check that the AST is right. And of course that um, along the way I found a few bugs and fixed them. I guess it was places where I forgot to use the array get reference. So that's I mean that's why it's good to have some tests, right? Just to especially for a compiler, I guess you should use as many tests as possible, as many examples, because if someone will use the language, they'll use it in a pretty weird way probably. So you better make sure that it's taken into account. So yeah, here you can see that all the types are shown for all the expressions and sub-expressions. Yeah, here I was thinking, well, should I put the type on the attribute? And probably not, because like in cool all the expressions have a return type, but attributes don't really do, because you cannot say that like you cannot have an expression with an attribute or a function. They are just definitions. So yeah, um, don't add the type there, but everywhere else you can do. Yeah, like you can add the types. It's safe to do that. And yeah, I don't know why I was so like I had a brain freeze when it comes about inherits. I was like, should the B be smaller than A or A smaller than B? In that case, like yeah, um, because it looks weird with the inherits word. I don't know why. Mm. Yeah, I mean, obviously, if B inherits from A, then A should be smaller than A in some way, if you think about it. Like A is the more generic type in the same idea. Yeah, here, for example, for the while loop, just delete when it doesn't work, and hope that the tests are enough, right? For the if statement, again, just delete what causes errors and keep only the good parts, and check that the types are there. Like that's the only important thing right now, just to check that the types are safe, because the type checking works, but before doing this part of the compiler, or like saving the types weren't really stored anywhere. I was just leaving them out, but just doing the type check. So yeah, for actually generating the assembly, or intermediate representation or something, we actually need the types to be able to, if you call a function on something, just to know which type it was, something like that. And yeah, I mean, I guess we are pretty close to finishing all the test cases. This was one of the more long. I guess this was a longer one, I wanted to say. And yeah, I don't know, I guess I found another bug. Oh, I was thinking, if the init from a let statement is not initialized, it usually gets the default value. But I don't think we have to put that on the AST. I think the AST should be kept as original as possible. So yeah, it wasn't working anyway, so I just deleted that. So if it doesn't have an initializer value, then it doesn't have a type to it or something like that. Because it doesn't make sense to have a type on the initializer, which is non-existent. Anyway, this was the 16th test, I guess. And yeah, I mean, the last four tests were pretty easy to make running. Oh no, I lied. This was the longest one. Which was it? Type dispatch. Yeah, but no, my logic was just delete everything that doesn't work. That's the best way to do it. And yeah, I mean, this point, I was just like, well, I'll just delete whatever doesn't work, and just get the AST, check if the types are there. And yeah, pretty close to finishing all the test cases and actually seeing if stuff works, or if stuff still works, because you never know what breaks when programming in C. I mean, it's a recurring theme for especially for the semantic check. It was really, you fix something, something else breaks, and yeah, it was. I mean, it was pretty funny to see that, but yeah. So I guess these were all the tests, and they are completed. So just making sure that everything has the right types, taking a bit longer on that longer multiple function calls in a chain, but managed to figure it out. And here, yeah, as I said, it's enough to just add the folder there, and it will run the test for it. And just to be sure that we got it, I also showed which folder it was. So yeah, I guess at this point we have all the test cases, and everything seems to be working fine. So just make a checkpoint, just commit everything, and yeah, just go to the next phase of the compiler, which should be generating the code in some way, like making the executable right now, because we have everything, the types, the AST. So yeah, we are basically good to go. Okay, so for the second part, we start out with an interface for the code generation. And as I said in the beginning, now we just have to build the tree address code implementation. So I started out with a function that should convert an expression from the AST into something else. And as you can see here on Wikipedia, it's like converting a big expression into a set of really like small expressions, but it's a lot of them, right? So and like the feature, like a feature of these expressions is that they only have three arguments usually. So like an addition, as you can see, it's the result is equal to a plus b or something like that. And the main idea is to convert all of our expressions in the methods, or in general, the expression, be able to convert an expression into such a set of really small expressions. And this is really similar to assembly in some way because um, in assembly you have usually three operands as well in some of the cases, and it's much easier to convert tree address code into assembly, or at least that's what I'm hoping, right? So and yeah, more interesting would be to convert um, control flow expressions into tree address code instructions, because they also require jumps and labels. So we also are gonna do that thing. And yeah, right now I was just thinking, well, which would be the best data structure for this problem? And with, I came up with almost the exact same thing as for the parser. So that's why I was pausing a bit, because I was thinking, well, but I don't really want to duplicate that code, right? Because it would be strange to duplicate it, I was thinking. But in the end, I guess that's the best way to have it, like have a triades code kind, like TAC kind, and then have a union with all the other expressions that you can have. So it's exactly the same as the expression from the AST in some regards. Yeah, as you can see, it was like the expression kind and then the expression itself. So yeah, and here I was just looking around at some homeworks that I found, like explanations for homeworks, and yeah, that's a bit helpful. Then I went ahead and implemented some unit tests in quotation marks because, yeah, I mean, we just have to be able to test that the tree address code works. So I copy pasted some of the older tests, and we are gonna have to write the references for them. So first, a test for checking that the identifier works. It's just a single identifier, and what we have to see is that this TAC generates an identifier basically. And yeah, now it's actually time to generate the triades code instruction, and probably the first one took the longest, although it's the easiest one, and that's just to create an identifier. And yeah, here I was, I think, yeah, that was the codegen.c file. So here we are gonna have a switch on the expression kind, and then for each kind of expression we have to do some stuff, right? So yeah, just go to the expression identifier, and there we have to call to this other function, because it's easier to just have another function for each expression kind. And yeah, I was thinking to maybe have a structure like TAC context, just because it's easier to also keep track of other required stuff, like um, you know, maybe we are gonna need some error handling or something, and we can keep information about that in the context. So yeah, for the identifier then, uh, yeah, here I was still just playing around with the code, and at this point I was thinking, well, how about being able to convert an entire AST into some kind of list of 3 address code expressions. But I think that still just having a function from expression to a list of TAC is better, because we might just call to that function when we want to generate the assembly. So here I was just again looking at this example function from a homework that I found, or like explanation for a homework or something like that. Anyway, um, more like the statement, right? So here, yeah, for identifier it would be pretty easy. We just have to say that the type of the instruction, we generate a single instruction basically, and the type of that instruction is gonna be ident, and this instruction will only hold a single value, which will be, let's say, the name of the variable, because it's a single variable, it already exists. But yeah, it took the longest because I just had to write like everything, right? Also the code for the other instructions, if you think about it, like all the cases and the main function, some idea. And yeah, here is, I guess, the point where I was thinking, well, let's also have a function that prints the like duck expression. I called it run at first, but I think I'll change it to print or something. And yeah, it just iterates through all the classes, then it iterates through all the methods, and I think also the attributes. And yeah, the idea is to take the expression that's used to initialize the whatever thing, like for example the method body, and just run the function on the method body. And yeah, that's the idea. And then yeah, we can print all the instructions from that were generated. Yeah, hopefully we'll see. I mean, the first example is pretty stupid because it's just a single x, right? The name of the variable that I put in the test case. So yeah, here I moved it to another file just to, because it's gonna take some space. It's almost the same thing as for printing the AST, which also has its own file because it was taking a lot of space. So yeah, for an identifier we just print the name of the identifier, and that's everything, I guess. So yeah, and then inside of main we just have to add a new argument for generating the, like for displaying the 3 address code, I guess. And yeah, fixing some of the last errors like compilers, and finally showing the result. Well, yeah, adding the argument and yeah, showing the result, which as I said is just a single x. So yeah. Okay, so now that we have the basics done, like all the wrapper functions, we can add more instruction kinds. For example, the integer, and this is going to be similar. And the idea for integer is we want to define a variable, assign that variable with the value of the integer, and then return the variable. So that's how the instruction set would look like. It's gonna have 2 instructions. The first one will define a variable for the integer, and the second instruction will just be the variable itself, like passing it to the next expression basically. So yeah, here I was thinking, should I use like a structure inside of the union, or should I type define the structure, like that's the idea. And yeah, I should type define it and then use it just to make it easier in the print of the instructions. So yeah, and here I was just fixing the printing, and then I went into the code generation, where I just, again, this is already explained in like that homework, and I could just look at that and try to copy paste it. But yeah, see here at this point for the TAC context, we need a temporary count because we are going to define temporary variables. And this is the first case where you use it. We have to define a variable t, and in this t variable we are going to put the value of the number that we read. And yeah, this is, I think, the first point where we actually convert from the string value for the int into an actual int. To be honest, I'm not sure why I did it. I just thought that it might be nicer to just hold an integer. Maybe we can do some optimizations, I guess. Like if we have an addition between two numbers, maybe we can, I forgot how it's called, but maybe we can convert it to a single number. So yeah, here at this point, as you can see, we were able to actually show that we defined t0, which was holding 1, and then just print t0 as the return, right? So yeah, and I decided that, well, let's also print the function name, because if we have multiple functions, then it's easier to figure out which one was used. Okay, and going further, we now can add the add instruction, and yeah, it's just gonna be, I guess, I copy paste the int, and what we have to do instead of assigning a single int is to assign two variables, let's say. So we have to define one variable for the left hand side and one variable for the right hand side. And yeah, this is pretty nice. First, I always just handle the printing just to get rid of it, and then for coordination, what's interesting about add is we have to first evaluate the left hand side, then evaluate the right hand side, and then do two new variables for the results and add them together. So yeah, here I was just looking around seeing how it's described, like the best way to do it. And yeah, first we have to evaluate recursively the left hand side and right hand side. So I reuse the tau expression from the beginning. And yeah, the idea is evaluate them. Um, this will make the instruction list a bit longer with like the required stuff that we need for the addition. And then we have to define this tag assign add, where we just add the results of those evaluation of the right hand side and left hand side. So here I just went ahead and made a few examples, and as you can see, when we have int literals, it generates the variables, and when we have the variables already existing, it just reuses them. So that's nice to have. Oh yeah, but I forgot to actually, I think I forgot to print them somehow, or I didn't. Mm. Yeah, to be honest, I don't remember how but I guess, yeah, I forgot to create the actual add expression. So now you can see that it also shows adding those temporary variables together. So for the addition, yeah, we actually define t0, t1, t3, and so on, and just add them together. I think the next one was the string and the boolean, which is exactly the same as the int. So yeah, those are pretty easy to implement. So just use some non-existing functions that we are gonna have to do, and yeah, I could just copy paste the integer, and that worked. So yeah, at this point I said, well, it's useless to have those test cases, I'll just rewrite them from scratch. So here you cannot really use stuff that's not already done. So I just had to use the true and just a single string, like string literal, for testing. And yeah, now at this point I had to also implement the printing of those things that we generated. And as you can see, it looks exactly the same as the int. So it's just the literal and its value. And I guess the name, like the type of the literal, so it was int or string. And yeah, at this point we can just implement all the other binary expressions. And here at this point I was thinking, well, should I copy paste this much code every time and implement subtract, divide, what else, multiply all differently, or maybe there's a better way? And I guess the better way was to just have a single binary structure. But then also I thought that, well, why should I keep inside that union, let's say, a different field for each one of them? So maybe we can just have multiple three-address code kinds, like a kind for addition, a kind for multiplication, and so on, and then have a single field in the union for the binary expressions. So it would be like, well, it's a binary expression and we know its kind, so we don't really need multiple, let's say, fields like in that structure. So it's enough to only have one, and we can specify the type of that instruction as an enum, right? So yeah, here I was saying that, well, we are going to implement all of them because they are all just binary expression, and we are going to have, yeah, instead of that, I'm going to change it to a single binary expression and a single unary expression, because it's not really needed to have multiple. It's, yeah. So the binary expression was already done for addition, and the unary one, it's basically the same, but instead of having to evaluate left hand side and right hand side, we just have to evaluate the single expression that we have, basically. But in the end, it's really similar, right? So we evaluate the expression, and then we have to return its temporary variable that we generated. So yeah, and I guess now I was just fixing the printing. And yeah, probably we'll figure out that it's useless to have. Well, it looks like I already did, so yeah. Yeah, and I guess I thought maybe it's better to just have a string there, just to make things look a bit nicer, with using the same keywords as the cool language. So yeah, it looked like the math like worked, and now I was just playing around with the, let's say, relational operators, which are pretty much also binary operations. So yeah, I saw that one of them was missing the smaller than equal, but it was fixed. And yeah, you can see that when I change it from a variable to a constant, it also defines its like temporary variable. Then another easy instruction to implement is the parenthesized expression, and that's just calling to the evaluation of the inner expression. So we don't even need a kind for it. It's just gonna be evaluating what's inside first, and then use that outside. So yeah, here I realize that well, I don't even need that kind, because it's just gonna print the expression as it is. So yeah, I guess at first I was just going with it, but yeah, then I was like, well, it's isn't it just calling to tag expression itself? And the answer was yeah, basically it is. So we don't even need a separate printing for it. So that's really nice. And yeah, I guess this is the best example for the expressions. And basically we have, you can see that in the f function we have like the variable x, then we have a parenthesized expression, then we add a division, and you can see that it starts out by converting the inner parenthesized expression. So it generates the value for the integer for 2. It generates a temporary variable for it. Then it does the negation for that temporary variable. Then it adds it with y, and only after that it multiplies it with x. And after that it does the division. It generates int 3 and then divides by x and then adds together those two variables. So yeah, and then just returns t6, which is the result of all of that expression. So, and it's also the return type of the function basically. So that function will return the result of all of those expressions. And I think that doing those expressions in assembly, it's much easier, like to translate it from the intermediate representation to the actual assembly code. I think that's easier. And then for G is really similar. We compute, like we convert the inner expressions from the parentheses, like x smaller than y, and we don't generate temporary variables because those two variables already exist. So that's one way to do it. And for the second expression, we generate the int, like the 10, and then do the comparison. And in the end, we compare the two smaller expressions together and also return it as t3, which is also the return type of the function. So yeah, I think it's much easier to convert from this intermediate representation to assembly than to convert straight into assembly directly. So this is a good first step, I think. Then yeah, basically continuing with the other type of expressions that we still have to do. For example, the is void or the new stuff, but here we just have to use our existing unary expression for is void, for example. Then new, it's also the same thing. We just have to reuse the, I guess, the unary expressions. And printing is also easy because it's just again using the existing unary expressions printing methods. So yeah, at this point I guess I also updated the checker just so we can run it easier, although it's not really needed right now. At this point we don't care about it, but yeah. And I guess the advantage of doing W error when we compile the code is that it catches those kinds of, well, you forgot to put inside of the switch, you forgot to put the cases for whatever you were using. So yeah, that's a good thing to keep in mind. Maybe try to use W error, although it's really annoying. And yeah, here a segmentation fault. I guess I forgot to print something, but I don't really remember what. So because its void was working, but new was not working. So that's what I was thinking. Oh yeah, I forgot to change the name when I copy pasted stuff. Well, I guess new was a bit different then, because instead of working with variables, I was working with types. Not really sure how it will play out when we convert to assembly, but I thought that, well, it doesn't really have to be one-to-one assembly, like it can be a bit higher level than assembly, like still using types and stuff, like weird operators and whatnot. But yeah, in the end, it's still a really simple intermediate representation for our code, for our expressions. And yeah, here I moved ahead and started to work on the assign expression, which I was thinking, well, it's really similar to doing the integer or something, because we're gonna have to evaluate the expression, or I guess it's similar to unary, because we have to evaluate the expression, then assign that expression to our existing variable, and then return that variable. So it has an extra step than unary. In unary we were returning the variable or like the result directly, but here we also have to assign it to the variable that we have in the assign. So it's one extra step. Yeah, but it's really similar to all of the other implementations. So that's why like doing the first, I guess, instruction took longer than most of the other ones, although these are more complex. Like doing a single ident was just getting this thing to return a single x or whatever the name of the identifier was, and that took basically longer than implementing arithmetic operations, like all of them together, basically, or even this assign. But I mean, assign was still pretty easy because we already have some code that we can copy paste. I guess at this point I was just refactoring stuff. As usual, uh, you refactor one piece of the code and then you find yourself in a rabbit hole of having 1000 plus minus changes, something like that. You know how it is. And yeah, I mean, at this point I was just trying to make the code look really similar, because it's gonna make it easier to copy paste for the other expressions like function calls and stuff. It's gonna be easier. It's also easier when you are using Copilot to have the code look, I guess, really similar to each other, because it's gonna make it easier to generate similar code down the line. So it's yeah, I guess refactoring gone wrong for some reason because the tests were failing. But yeah, now it was working. So here I was just checking out if the sign works, and basically it should work as the math expression, but with an extra step of also assigning the value of the expression to some variable that we have there existing. And yeah, at this point I was thinking which instruction to do next. I guess the let expression would be easy, or maybe the block one, because it's yeah, I guess the block expression is just a for loop over all the expressions inside, and what you have to do is evaluate each one, and if you are on the last one, you just have to take that thing that you defined as a result. So basically, as in the book for the cool, like in the manual, it says that the block expression returns the last instruction that it runs, right? So if we do some random instructions, we should see that it returns the temporary variable for the last one. So here it was x plus y, and it returns t1, which is the last one. And yeah, at this point we were left with just the function calls, the let statement, and the conditional operations. So I thought that, I guess the easiest one to do at this point is let, and then the easier ones still are the function calls, and only then the conditional operators. So for let, started out by copy pasting the block because we are going to have again a for loop over all the initializations, right? So we initialize all the like variables, and I guess if the init is not null, then we have to evaluate the expression, and otherwise we are going to use, I think we are going to use the default value. So here we like evaluate each expression, assign the value to it. I think I copy pasted from assign. So we assign the value that we got for the expression to the variable name. And then here, yeah, I was thinking, well, if we don't have an init, then we can use new for that. So yeah, basically we are gonna use the init, and here we are gonna use a new statement to define the, I guess, the default value, because if you do new int, you're gonna get a 0. New string, you get an empty string, something like that. So here we use new for getting the initial value of the let statement. And yeah, I guess after getting all the inits, what's still left to do is to evaluate the body of the let statement. So that's what I did here, evaluated that, but I think I forgot to return the value itself. So it should, yeah, here when we generate x, see it's gonna use new int, so like the default value, but I think I forgot to actually return z, although in this case it's fine. I don't remember exactly why. Anyway, oh yeah, because I recursively call to expression, right? So it's gonna handle whatever it's inside basically, so we don't have to do that. So yeah, here for the function calls we have to define two types basically, but I think I only did one, which is fine because it's gonna be the exact same thing. We are gonna need to evaluate the expression on which we make the dispatch, and if it's a simple function call, then the expression is gonna be self. Then we are gonna need the type like on which we call, like the type of the expression, which is just gonna be, in case we don't have it, it's gonna be self type. And yeah, then we need the method and to evaluate the arguments. So yeah, here I did identifier, which is gonna be the result, then a dynamic array of chars, which is gonna be, because first we are gonna evaluate all the arguments obviously. So I created two functions, one for the dispatch and one for the simple function call. So we can implement them in parallel because it's gonna be similar, but I guess the idea for both of them at first is to evaluate all the arguments. Like that's the first thing. Even in like any programming language, when you call to a function, the first thing that's executed is, I think, the evaluating the arguments, right? So I guess that's the idea. So we can do a separate function just to not, no, just to reuse it in both of them. So we go through the arguments, call recursively to TC expression, and put the results into that list. So we're going to have a list of temporary variables, and each temporary variable will hold the evaluation of each expression, right? So that's the main idea there in the function calls. So I guess we implemented both of them in parallel. So evaluate the arguments. Here I thought, well, we don't really need that to be a pointer. It's not, it's useless to have a pointer. So yeah, the first thing that's different is evaluating the expression in the like full dispatch, I called it, like in the function dispatch. And yeah, here if the dispatch type exists, then we use the dispatch type. I guess otherwise it should be self type or something. Well, I guess yeah, the type of the expression actually is not really self type. And in the end, yeah, we have to create a new variable. And I think I forgot one of them, but yeah, we'll see afterwards. So at the end, we just return the value that we are gonna get when we evaluate the function call. And in the simple dispatch, again, because we don't have an expression or a type on which we do the dispatch, we just use self and self type. I hopefully that's how you do it, but I mean I'm not sure because I haven't done this part already, so I cannot tell if it's gonna work or not. But my guess is that that's the way to do it for simple function calls, because I guess you call it on self, but yeah. And as the result, we want to see the expression on which we call the function, and then the type on which we make the dispatch, and then the function name and the list of arguments. So here we define some stuff just to have it, and when we call b.f of x and y basically, so we want to see um, those things. Yeah, and here I think I forgot to put the method name in the dispatch call, so just put the method name, and now we see the call as it should look like. And if we call the function directly on a, we should see something like that. And if we call it like like a function call, we see that it's gonna be self at self type, and then we call the function. So yeah, I think that's how it should look like. And yeah, hopefully that's gonna make it easier in generating the assembly. Although I'm still not sure how to do it for function calls, but I mean, in my opinion, that's how it should be like. So you get the expression, the method name, and the arguments. So what more can you need for a function call, right? It's still gonna be a jump as the ifs and while, so it's fine. Okay, so I guess now it was the next day, and I decided to work on the conditionals. So on the if and the while, basically, and also the case statement, which I guess should be the hardest one, but we'll see. So first, we need a label, uh, unconditional jump, and the jump if true. So those are the three things that we need to be able to implement. Well, I guess to implement an if, we just need the label and the jump if true. But for while, we also need an unconditional jump. So that's the idea. So yeah, to implement the if statement, as usual, we just define its structure and the function that we're gonna use. So yeah, it's gonna take in the condition node. So first we have to evaluate the predicate, so we can just reuse some existing stuff, but yeah, we have to evaluate the predicate. So yeah, here I was just saying that I don't think that's the best way to do it. We might need um, like the label, a single label for jump, and the jump if true instruction, which is gonna be the the expression to check, or like the expression to check is more like the variable name to check if it's true, and the label where to jump. So at this point, as we did for variables, when we generate a single variable, I thought, well, we might need to add that to the context. So basically the label count this time, and be able to generate labels like we generate temporary variables. So it's gonna be like label count, and here we need a function to generate labels. So it's gonna be this new label, and yeah, this gives us the then label. So for the if statement, the main idea is we evaluate the predicate, then we are gonna have a jump if true, right? Jump if the predicate was true. Then we are gonna need a then label somewhere a bit lower, and we jump to that label basically if the predicate is true. And otherwise, we would have the else statements right after the predicate. So if the predicate is not true, we are not gonna jump to the then label, we are just gonna fall through and execute all the code for the else. And when we finish the else, yeah, here I guess we need an unconditional jump to the done label, which is gonna be below the then, right? So it's first it's gonna be the else content, and after the else content it's gonna be the then content to execute. So that's the main idea here. We evaluate. I guess I also added some comments just to make it more visual, but I guess at the end just yeah, I mean whatever. But you can still see from the way I coded it that it was like evaluate the predicate, do the else stuff, then do the then stuff, right? So yeah, basically branch if true to the then label, then we have the else part, then we have the jump to the done, then we have the done label, then we have the then stuff, and then we have the done label. So that's the idea, right? That's usually how people implement if else in assembly. So I mean that was also I guess on the Wikipedia page. But well, on the Wikipedia page I think it was a for loop. But anyway, doesn't matter. Yeah, I guess that's the way people usually implement if then else statements in assembly. You first need the predicate, then you need the else, and I guess I'll just stop and explain it on the example itself when I get there. So just printing the stuff, now implementing the printing functions. I mean that's pretty easy. So and yeah, just showing everything. So obviously some semantic errors. Yeah, so I'll just have them side by side because it's easier to visualize. So for example, for the last one, you can see that we have an a.h on the right side. That's where the function begins, right? So we have the evaluation of the predicate, which is just an is void x, and t1 is the result. So then we have a branch if true, the bt, that's the name of the instruction. And if this t1 is true, then we are gonna jump to the L0 label. And yeah, L0 is almost at the bottom, you can see. And we say that T0, which is the result of the if, is gonna be equal to X, which is just, you know, on the then case. And then finally, if the branch if true is not taken, if we fall through it, we are gonna execute the code for the else. So it's gonna do int 100, which is the int constant, then it adds it to y and then subtracts x from it. And then it also says that t0 is gonna be equal to whatever that math operation was. And after it finishes the else, it's gonna do a jump to label 1. And at the end it returns t0, which as I said is the result of the if. So that's the main idea of the structure of an if statement. You evaluate the predicate. If that's true, you jump to the then label, and if it's not true, then you execute the code for else, and when you are done with else, you jump to the done label. and at the end, because school is an instruction, or I forgot how they mentioned it, like expression-based language. The if statement has a return type, which is either of the branches. It's like in Rust where you return the value of the if statement or something like that. So that's the main idea. Then yeah, I did a bit of refactoring, basically just because there we have char pointers, and I thought it might be better to have structures for them, just in case we need to change them for some reason. I don't know. It happened to me before, so I thought, well, just do it now, and it's easy to still change it before we actually add the while loops and stuff, because then we are gonna have more changes to do. So it's easier now that we have just the ifs. And yeah, all the tests run. So at this point we can go ahead, make a checkpoint, and yeah, I guess I still had some refactoring stuff to do for identifier for some reason. I don't know why I decided to do that, because I guess it was fine. But yeah, anyway, just changing from char pointer to a structure. Uh, that took a bit because I had a lot of places where I used identifier, which is obvious because almost everything, like almost all the instructions or I guess expressions, were returning some value. So almost all of them were using the identifier, which is interesting. I don't know. So yeah, here I was just refactoring the code. In the end, it was useless because I haven't changed the identifier. But who knows? Maybe for the next stages, it's gonna change or something. So yeah. So yeah, I mean, I'm probably just gonna speed up through this entire process of refactoring because I mean, it was just fixing the compile errors. It wasn't really anything interesting in doing that. And yeah, I guess we can now wait and move next to the while loops. So yeah, so I guess the while loops, these were explained on that Wikipedia page, but it's still gonna be similar to conditions. And yeah, I guess the idea here is we're gonna have the predicate again. We're gonna evaluate the predicate. Then we have to check if it's not true. So we have to create an extra, what would we call it? It would be like an extra variable, like a temporary variable, that it's gonna have not predicate inside of it. And basically, if the predicate is not true, we are gonna jump to the done label. So there I created the, uh, let's say, not predicate, where I just copy pasted from the assign not, pretty straightforward. And just there I guess I forgot to add it to instructions, but not really important. Anyway, if the predicate is not true, we jump to done, and otherwise we compute the body, we evaluate the body, and at the end we jump back to the loop. So we jump back to the evaluating the predicate again, and that's an unconditional jump, right? So it's gonna be executed every time basically. And yeah, just fixing, I don't know, some random errors, and at the end I just returned the value, although I'm not really sure what the loop returns because it returns an object type, pretty weird anyway. And yeah, here I was just fixing the errors in the test cases for whiles. It should be while loop and pool, whatever. And yeah, checking that everything was working fine. And yeah, as I said, this example was also shown in the Wikipedia page, so it should look exactly the same. So it's evaluating the predicate, then the body, and then jumping back to evaluating the predicate. So that's the main idea. We have to evaluate the body multiple times of the while loop. I guess that's why it has to return an object type, because you never know if you have ifs inside of whatnot and it returns some random stuff each time, then which one do you return? Like the last one or the combination of all of them? So I guess that was all for the while loop. And yeah, I guess the last one was the case expression, which I thought it should be the hardest one. Probably it was the hardest one. Just because it had a lot of you have to create a lot of labels to make it work. So yeah, here I was just thinking, well, can I run it on my main.cl file? And I guess not really, because I haven't implemented case. Obviously, I just have to implement case, and that's not ready yet, so it cannot really work. So yeah, we first things first, we create the identifier, which is gonna be the return of the case, as we did in basically all of them. Then we have to evaluate the predicate, but here it's more like the expression, the case expression or whatever. I have no idea how it's called though. And afterwards we have to do a for loop over all the branches. So I thought it was called branches, but I guess it's called cases. Anyway, so we go through all the cases, and here I thought we need some extra instructions, like for example isInstance. We need to check that the expression that we get is an instance of the specific type. And yeah, basically that's the first thing I did there. So check that the I guess the expression that we got in the first step has the type of the current case, right? I think that's the first step. And probably how this case statement would look like the main structure of it, is we evaluate the expression first, then we are gonna need multiple jumps in a row. So first we have, if each instance is actually true, we jump to its case label. And I guess this is how you would implement an if in assembly if you were doing it for the first time. Like, have a lot of jumps basically. Have a jump for then, have a jump for else, that's how I imagine someone would do it. But here I guess if the the instance of the expression is the correct type, we have to jump to its specific label. And here we are gonna also need a list of labels, because first we do the jumps and only afterwards we can do the actual, let's say, bodies of the branches. So yeah, the main idea is, I guess, yeah, there I was just doing the print, and now should fix some of the errors. So yeah, we get the right instructions for the type, like for is instance of, but now we actually need the labels and the jumps. So let's see. I just wanted to simplify a bit the test case. So you can see that we get the types, or I guess the result of checking if the expression is the right type. And yeah, here just debugging, thinking how can I do the jumps with not that many jumps basically. But the easiest way, as I figured out, is just have a jump for each case. So there we have the branch if true. We don't have yet the labels, so we store the labels that we generate in there, and then we do another for loop after we finish this one. This is like the first one is the generation for loop where we generate the labels, and here we actually put the labels in our dynamic array of instructions. So we put the case label, then we put the body, the evaluation of the body, and then we put a unconditional jump to done, basically. And at the end we have the done label. So I guess a segmentation fault because I forgot to initialize the list. And yeah, there we have the jumps. But you can see that we have some random variables like x and I guess some strings, some stuff that we use that we don't really have defined there. So it's those variables, right? So what we have to do, I was thinking I should maybe try to cast them to the correct type and also define a temporary variable for them just to have them used in some way. So basically inside of the body, when we evaluate the body, I also wanted to define this temporary variable and use this cast operator, but I'm not sure if, again, if that's the correct type, like the correct way to do it. But I mean, it's still not assembly yet, so probably can do whatever we can do, probably whatever we want with this thing. So yeah, here we actually have this comparison between the cool code and the intermediate representation, and basically, as in the case of the if statement or the while statement, the first thing was to evaluate the expression, but in this case the expression is just value, so it's not really evaluated to anything because it's just a simple identifier. But the next thing was to go one by one through the cases and check if the value or like the identifier, the result of the predicate, is instance of whatever type is present there in the case. So the first thing would be check if value is instance of string. If that's true, then we would jump to label L1, right? If it's not true, then we would check the next case predicate, which is value is instance of object. And if that's true, we jump to L2 label. And yeah, basically that's the main idea. We check the case label. If that's true, we jump to its specific label. And that's why I said that this is the noob way of doing an if, because it has a lot of jumps. But yeah, the first thing is then like after these jump conditions, we have the labels themselves. So L1 would be evaluating what's inside of the branch and assigning to T0, which again is the return type of the case, assigning that result, and then jumping to the done label, which in this case it's going to be called L0, right? So it jumps to L0, which is the done label, and returns the result of the case. And the same thing would be done for L2 label, which is the second case. It executes what's inside of the branch body and jumps the done label. That's the main idea of the case statement. It's really similar to if. It has like evaluating the predicate. If they are true, you jump to their specific label, and at the end you jump to the done label. So pretty basic control flow stuff, I guess. And yeah, I guess at this point we were done the with all the expressions for the cool language. We done like the basic ones and also the control flow ones. So I guess 15 test cases was enough for this part. And yeah, I guess we were done with everything there. So now we were actually able to also run the tree address code generation on our main.cl file, which is a bigger one. And yeah, I mean, you can trust me that it was working. It was generating the right assembly code. So I guess for the next parts, we are ready to actually take this tree address code and convert it to assembly. And that's gonna be more interesting because that's the final part of the compiler. Maybe also do some optimizations, but trying to get to assembly is now the goal because that's gonna make us able to execute the code. So see you there.